Okay, population growth and interactions, chapter 20. As you can see, there's a number of things here, and we may actually have to break this down into three short little videos. Growth patterns. Students will explain quantitatively the change in population over time. Okay, describe growth pattern populations in terms of mathematical relationships among carrying capacity, biotic potential, environmental resistance, and number of individuals in a population. Well, with growth patterns, the first calculation you're going to do is calculate the change in numbers. That's determined by the births. So natality is another term for birth. So in French, nat means birth. In French, mort means death. So we put that as a D, B, and a D. Immigration, think of immigrants. They're people coming into Canada, moving into the population, okay? And emigres are people that have left the population right there. So when we do a change in population, our formula is delta N means change. We're going to add the pluses, the births plus the immigration, and we're going to subtract the negatives, which are the deaths plus the emigration. Growth rate. We're going to take the change in the number of individuals in a population divided by the time. And if we get a positive result, that tells me that my population is increasing over time. Per capita growth rate, CGR. What is the average growth rate per individual? That is what this per capita growth rate attempts to explain. Now, it's better phrased in this way. Per capita growth rate gives a rate of growth that is proportional to the number of individuals in a population. If the population is really big, like 2 million people, and you have an increase in 4,000, that's not a very big number. But so it's in relationship to the large population of 2 million. But let's say you have a population of 10,000 people, and then the next year it grows by 4,000. All of a sudden, that tells me that there was a very large increase in population. And that's what the per capita growth rate does. It provides the context for the growth relative to the original number of individuals in the population. Change in number of individuals is the final minus the initial numbers. Population density is the number of individuals in a given area divided by the area. But if it's in a lake, for example, we would need the volume. So often this is going to be, say, meters squared, but volume will be meters cubed. Now, related to this is this concept of distribution patterns. Patterns of populations can be clumped, where the population is clumped. They can be evenly distributed, or they can be random. We don't know exactly where they are. There's no set pattern. If I was to do an aerial survey of moose, this would be random. They seem to wander. Whereas I look at the human population here, we would see that as clumped. High distribution in the eastern seaboard and Europe, nothing in sub-Saharan Africa almost, or where I come from, the Northwest Territories. Very little. So it's clumped. A lot around Southeast Asia, around coastlines, India, okay, and so on forth. Now, evenly distribution would represent these cactus. They're evenly distributed apart because of a key limiting factor in water. So let's take a look at sample problem here. Collared pika, these guys are actually related to rabbits. They're found in the mountains. You might have seen them. They're really cute. So rock rabbits. The population dropped from 25 individuals in 1998 to 5 individuals in 2000. Calculate the growth rate from 1998 to 2000. Well, we first of all calculate our change in numbers. Now notice the final number minus the initial is going to give me a negative number here. And my change in time is 2 years. So when we substitute into my growth rate, I have negative 20 individuals over 2 years, negative 10 individuals per year. A population of caribou, 26 caribou, was introduced on a predator-free island in Alaska in 1910. For the next 25 years, the per capita growth rate of the population was 75.9. Remember, that's going to give you a number relative to the original population. In about 1934-5, resources became limited and the population crashed. Calculate the number of the caribou on the island just before the population crashed. Let's see what we've got to work with here. Here's my formula, but they're trying to find the change in the number, calculate the number of the caribou on the island just before. And we've been given per capita growth rate and the original number. So we're going to substitute in 75.9. Notice there's no uh, um, variables here as opposed to here, caribou, 26 caribou. So we get an original number of 1,973. But we have to add that. That's the change in the caribou population. Now we have to add it to the original population to find out what the population was like in 1935. So there were about 2,000 caribou on the island just before the population crashed. Now I encourage you to do this next step. Check your solution. 2,000 minus 26 caribou will give me 1,974. And we work this backwards. 1974 divided by 26 will give me my 75.9. Okay, factors affecting population growth. Biotic potential is a maximum number of offspring that can be produced in ideal conditions. So it's regulated by the number of offspring, how many times an animal can reproduce in a year, capacity for survival, chance that they'll reach reproductive age, maturity age at which reproduction begins, length of the life. Okay, so compare, let's say, mice with bears. Mice will have a very high biotic potential because they produce about 6 pups per litter. They can do it several times a year. This would be lower, but it wouldn't offset the other variables. Mice, after a few weeks, will be reproductively capable of reproducing, and this would be fairly short. Okay, but compared to a bear, the biotic potential is very low. Bears only reproduce until they reach the age of about 3 years old. 4 years old. And then the mother bear will only reproduce every 3 years or so because she looks after her uh, bear cubs for a long period of time. So the biotic potential for bears would be very low compared to mice. So we say this is R. And we're going to get to this concept of R selected a bit later on. Environmental resistance. It's all the things pushing down on a population, keeping it in check, preventing it from going up, up, up. Okay, so we can see here for fish, it would relate to oxygen, food, disease, predators, limited space. And limiting factors that affect population growth, they can be density independent. They're going to affect population regardless of size, and they're mostly non-living. So they'd be things like natural disasters and unusual weather. And density dependent, this relates to when a population reaches a certain density. So more fish in the lake, for example, there's going to be more competition for food. That's going to attract more predators. And being closer together will attract more diseases or parasites. And related to this is the law of minimum. And this bucket is a good example. Of all the essential substances required for growth, the one in the shortest supply is going to limit population. A good example of this would be scurvy and vitamin C. You only need a little bit of vitamin C, but if you don't have it, it is going to significantly limit the population. What does the barrel represent? What does the water represent? So I want you to think about that, and we'll come back to those discussion points uh, during our meetup. Oh, here's the answers. Okay, essential substances and population growth. Just as the capacity of a barrel with staves, these are these wooden struts here, of unequal length is limited by the shortest stave. So a plant's growth, for example, is limited by the nutrient in shortest supply. Carrying capacity, last concept, the maximum population size of the species that the environment can sustain. And populations that are K selected, the letter here is K, tend to fluctuate above and below the carrying capacity, K, right there. Now, we'll take a look at our bears, for example. In southern Canada, the carrying capacity would be fairly high compared to, say, northern Canada. Why? There just isn't as much food. So that would be a southern population of bears. And this would be a northern population of bears. So carrying capacity varies based on the environment. Okay, and it has to do with all these limiting factors. Okay, will determine how high the bucket can go, carrying capacity. Okay,